Thanks everyone for coming. So it's my pleasure to introduce my colleague Roni Harnik as this week's IQUIS speaker. I first met Roni kind of doing more traditional particle theory phenomenology, but now we're colleagues in the SQMS Center at Fermilab, trying to use all kinds of fancy new quantum tools to do searches for new particles in dark matter. So Roni got his PhD at UC Berkeley. He's been a staff scientist at Fermilab for several years and is now the quantum sensing theory lead for the SQMS National Quantum Center. And I'm really excited to hear about all the interesting stuff he's been doing with nonlinear optics, looking for new particles. So thanks.
Thank you. So a few words before we get to the actual physics. Last week I got a cold, and then I gave a talk to high school students about dark matter, and apparently I got really excited, and I lost my voice. So if this talk would have been on Friday, you would have heard nothing. So I'm hoping this will sort of head out. If not, feel free to come close and strike the right balance between not getting my cold and hearing. And I'll let you, and I'll stay hydrated. Yeah, so I work at Fermilab, the particle physics lab. So that's sort of where my background. Yoni and I come from this sort of ilk. Let's say the same for Patrick, and Aida, we're close cousins. Yes, Jesse also, yeah, quantum technology or technology in general is keeps on coming, and sort of work is involving sort of at the interface of theory and experiment. At Fermilab, we have this center, SQMS. Let's see if the clicker works. Yes, which is all about superconducting cavities and superconducting systems, high coherence 2D and 3D superconducting systems. And I'm not going to tell you about any of that today. Actually, I'll tell you about stuff that I was working on before. Which is related to optics. So this is actually not related to that. It's funding-wise, it's related to that. Wonderful. The work is mostly based on this paper with experimental colleagues, more detector people, not necessarily optics. I'm working on a follow-up. This was my pandemic project, so that's by myself. And there's an interesting related work. I'll highlight Christina, who may or may not be in the room, but Christina is a postdoc here and at Fermilab, superposition. Very good. Wonderful. So I come from the particle physics lab. So particle physics is about understanding it's about understanding everything, right? But it's about understanding what everything is made of. And we have a wonderful, successful model for all the menu of particles that we know that exist. The standard model of particle physics. Add a little gravity to that, and that explains a whole lot. And it leaves a lot of open questions. What's the dark matter that seems to be around? Why is there more matter than antimatter? What are the symmetries of these interactions? Are these this soup of interactions? Do they unify, et cetera, et cetera? Maybe I'll bring my computer closer. Good. So we have all these questions that we are curious about. And in addition, we're broadly interested in the question, is there anything else that's not on this menu, but actually exists in the rulebook, in the degrees of freedom that we can excite? And if there is, maybe that's the dark matter. Any discovery of any new item on this menu will lead to profound new understanding. And so what I'll tell you today is that optics experiments, nonlinear optics experiments, in principle, maybe, this is, so I'm a theorist, these are very much proposals to some degree in their infancy, but maybe optics can join the search in a direct way. So just to give away the punchline, the idea would be, so in collider physics, often one of the ways to look for new physics is that we collide particles. If we know the energy very well, that's one way. The energy in all directions, that's a great way to do it. And then you measure all of the energy coming out, and if there's missing energy, you discovered an invisible particle. Now, the Standard Model has invisible particles, neutrinos. I'm contractually obliged to mention neutrinos coming from Fermilab. But there may be others, like the dark matter particle. So missing energy, or missing momentum for that matter. Something observable going one way, traded in association with something else. That could be a cool way to search. I would like to bring this technique to the optics table. And so the idea would be to introduce dark SPDC. SPDC stands for spontaneous parametric down conversion. And that is one of the workhorses of quantum optics and optics in general. So SPDC is the process by which a pump photon converts to two photons. One is called signal and the other is idelr for some reason. So I speak optics with a heavy accent, and I've grown accustomed to some of the quirks of the terminology, but I find it it's an interesting choice of words because the signal is going to be our signal, and the idelr is idelr, and it's going to be super idelr. It'll be an axion or a dark photon, something that's really, really idle as opposed to idle by choice. So it's in this case the quirky technology is a good fit. So that's the idea. But I'll give. So here's the plan for the talk. Because this talk is both about optics and high-energy physics, this talk sort of needs two introductions. And this is, by the way, one way is I was really excited about coming to a place that has both high-energy physics and optics experts, because here I get to try this paper that I'm working on to see if the introduction. So let me know if it does or does not. Be candid, please. So introduction number one will be an introduction to optics. I'll apologize to all the optics experts, but I'll do it with a particle physics mindset. So hopefully the optics people will learn not about optics, but how particle physicists think, and that'll be an interesting anthropological experience. So I'll talk about optics as an effective field theory in our weird language, and I'll talk about nonlinear optics in the same language. Then I'll switch gears and I'll talk about the new physics models, but I'll try to speak like as an optician would. So I'll talk about new physics beyond the Standard Model, extensions to optics. One will be linear, the other will be nonlinear. Dark photons and axions. And then I'll talk about the process itself, how one goes about calculating the rates, some of the fun subtleties involved, if there's time. And the rates will be low. Very good. So optics, optics is the low energy effective field theory of light traveling through a medium where the medium is made of atoms. So here are many atoms that I collected off of the web. There's some lengths and frequency scales associated with this medium. So again, particle physicists like to keep track of fundamental constants. So the frequency of exciting an atom is Rydberg, which up to maybe a factor of 2 or 4, I don't remember, is alpha squared times ME. the distance between the atoms is the Bohr radius, roughly. So alpha times ME, just one alpha here, two there. So that's the medium. By the way, there are many atoms. So if you really wanted to keep track of all of the degrees of freedom here, that is an impossible task. But that's the wonderful thing about effective field theories. You get rid of most of the degrees of freedom. And then there's the light. The light, we'll take it to be, well, the light was emitted by some laser, which is also related to atoms or molecules or something like that. So the characteristic frequency will also be alpha squared ME, but we will take it to be lower than the excitation because we want this to be a transparent material to this light. That's the frequency of the light. The wavelength of the light is also set by the same parameters. I apologize, the H bar and C are one throughout the talk. I think I apologize explicitly somewhere. So that's one thing that particle physicists cannot really get rid of. But this is a micron, right? And this is, whereas this is an angstrom. So I gave away the punchline of the next lick, which is the atoms are very closely spaced together as compared to the wavelengths of the light. So the atoms react to the light in a very collective fashion. And that has implications. So first of all, if light were to, let's consider forward scattering, the amplitude, the quantum amplitude for forward scattering, just light interacting with the atom and going along its merry way in the same direction. The amplitude to forward scatter off of a single atom will be small, of order alpha. But remember, we're collectively scattering off of roughly alpha, right? There was an alpha difference between the density of atoms and the wavelength of the light. So that alpha can offset this alpha. So the forward amplitude for scattering off of a medium can have an order one effect, right? And lo and behold, we see order one indices of refraction in optics and not order alpha. So that's a wonderful thing. And of course, we can start talking about the medium sort of in a systematic effective field theory way. And so the mean fields that we need to consider that have to do with the medium, not the 10th of the 23 atoms, we can just think of these fields and we'll get rid of magnetization, but the polarization and magnetization densities. This discussion, by the way, is buried somewhere in Jackson. I didn't make this up. In a very, also, high-energy electromagnetic person at that interface. Wonderful. So really all of optics from my linear optics, from my point of view, there's incoming light. It interacts with some dipoles that are oscillating, that as a back reaction, they induce radiation. These are oscillating dipoles now. They're oscillating because of the light that induces emission, and there's interference between the incoming and outgoing light, and that leads to the index of refraction. So this reaction of the material in response to the electric field, this is sort of the polarizability. This is usually equation one in sort of a linear or nonlinear optics book. Wonderful. Now I'm moving very slowly, but it begs for a high energy physicist, this is sort of there are some really surprising features here that we usually take for granted, but I like to say them anyway. So here's the index of refraction where it appears in the wave equation, right? It just affects the speed of light, if you will. And that affects the dispersion relation, the relationship between momentum and energy. Momentum and energy, these are kinematical variables for a high energy physicist. That's what these are. However, the indices of refraction can depend on many, many things. Usually for us, the electron has one dispersion relation, and it's pretty difficult to change it. But here it's very easy. So it can depend on the frequency, the propagation direction, the polarization, the temperature. I was reminded this morning in Paul's lab. So many things can affect this index of refraction. So for example, in the low energy effective, imagine you're a thing that lives in this low energy effective field theory. A photon with one polarization and a photon with different polarization are literally two particles with different flavors, right? And I'm deliberately using the word flavor because in particle physics, the word flavor has a technical meaning. That's the quantity that changes when you switch an electron, say, to a muon, which we usually say are different particles. So the analogy is that the electron, the muon are also 2 degrees of freedom and all they differ by is they're orthogonal and they differ by their dispersion relations that in this particular case, they have different mass. These 2 photons in a birefringent material have different index of refraction. But this difference in mass has a lot of impact on phenomenology for a particle physicist. For example, a muon can decay to an electron because it is heavier, right? And indeed, in nonlinear optics, a photon can decay to other photons, okay? Only they call it down conversion and not decay, but it's the same thing. And what else? Okay, so that's good. So how can a photon decay? So far, I told you only about linear optics, but the index of refraction appears from the EFT point of view at, pardon my language, at the renormalizable level of this effective field theory. But like any effective field theory, it will have a cutoff, and it is very sensible and very natural to introduce higher dimensional operators that are suppressed by the cutoff. So the field that is most convenient for use here is the E field. So here is a dimension 6 operator that you can introduce to the Hamiltonian. One concession is that in doing this we abandon Lagrangians and go to Hamiltonians. So this is dimension 6 operator, a dimension 8 operator. This is responsible for spontaneous parametric down inversion. This goes by the name of 4-wave mix in optics. And these are interesting tensors that are properties of the material. Again, as particle physicists, we can't help but first of all, comparing to the medium that we're used to, which is vacuum, and also to use some of our jargon. So we can use what we call as naive dimensional analysis, which is to estimate what the sizes of these coefficients would be. So if the E field were of order of the E field in an atom, which is roughly the charge divided by the Bohr radius squared, I plug that in, and if I require that the dimension 4, the renormalizable, equals the dimension 6, the dimension 8, that is what in NDA, that is what I would use to estimate these coefficients. And this is roughly how large this would be. It's fun for us to compare it to vacuum. So in vacuum, chi2 is 0. This is so well known. It has a name. It's called Fourier's theorem. So this is a consequence of charge conjugation. So this just never happens in vacuum. But by comparison, this term is the just light by light interaction in vacuum, which comes from a loop of electrons. And this has 2 alphas upstairs. This has 5 alphas downstairs. So this is many, many orders of magnitude. And this is obviously a consequence of the fact that this effective field theory lives in a background of 10 to the 23 atoms per centimeter, and the vacuum is in the vacuum. Okay. So this is my rendition of optics. Apologies for the if I butchered it, but this is how sort of I think about it as a particle physicist. Questions, complaints, concerns? Okay, yes. Right, but this block of crystal that I'm living in is not Lorentz invariant, right? If I boost it, all these 10 to the 23 atoms will start moving. It's not necessarily rotationally invariant. And if it was rotationally invariant, for example, if it was centrisymmetric, this would be 0. This only exists for non-centrisymmetric crystals that violate parity, for example. So, and that's why, yeah. So none of the stuff that we're used to, just Feynman rules, go out the window. You need to calculate, like, just use Fermi's golden rule and calculate, or whatever method you prefer. But the symmetries are, most of the symmetries that we take for granted in the vacuum are not there because we're in a lab and there's a crystal. Yeah. Yes. Yes, these two. I didn't write them down as. Yeah. So I estimated these by just saying that this term would roughly equal that term if all of these E fields were roughly the E field in an atom, because this is generated by atoms. So that's sort of a naturalist argument. Again, this is not, I didn't invent this. This is probably in Boyd. To within an order of magnitude. Paul, do you know? Is this close enough? Or, yeah. This is an order, a good order of magnitude estimate, but the units for this, for example, are usually picovolts, meter picovolts, or is it picometer per volt? One or these other, but it's an inverse E field. Yeah. Of course. Yeah. So for example, chi2. Yeah, chi2 again for a mirror symmetric material. Chi2 is 0. So there you go. Many orders of magnitude difference. But this is again, this is at the level that you'd expect me to estimate anything. Wonderful. So now so everybody knows optics now, including the high energy physicists. Now let's talk a little bit about high energy, really low energy physics, because we want to introduce new particles that are going to be produced on shell on an optics table. So the masses of the particles had better be an electron volt or less. Okay, that's fine. They'd better be pretty weakly coupled to evade detection, but we're by now, at least us particle physicists are quite comfortable with that. So you all should too. So again, and the MO for beyond the standard model physics is literally that you go beyond the standard model. So you make a hypothesis, a well-defined hypothesis for what the new physics may be. So because we're going to work with optics, we're going to extend optics, and we have two logical possibilities for how to extend optics, either linearly or non-linearly. Okay, so let's talk about the linear extension. A linear extension would mean that the Hamiltonian will remain quadratic in fields. So one of these fields will be a photon, the other will have to be this new particle. In order for these two to mix, and now this needs to happen in the vacuum, so all the symmetries need to be respected. So this needs to have the same quantum numbers as a photon, and that's why we call it a dark photon. So it's just another photon. So the hypothesis, we add another photon to the rulebook, and we're going to give it a mass. Turns out that if we don't give it a mass, I can just redefine what I mean by a massless photon. The electron only talks to one linear combination of the two fields, and then I've done nothing. So it also needs to have a mass. That is, again, possible. So why would I do that? What grand reason would I have? Why not, right? So first of all, here, I just did it, and you can't stop me. But historically, again, if you look at this, there are several copies of the same particle. We've already alluded to the different flavors. There are several copies for no good reason. The muon, who ordered that? All that stuff. So this would not be, I mean, looking at this, this would not be a surprise, except it would be immensely surprising. But of course, if we did discover this, it would teach us some profound things. Maybe this is related to dark matter. This is a new force in nature, a long distance, but by some scale. It would have, so if you want to unify the forces, here's another one for you to unify. So it would teach us something important. Okay, so under the hypothesis, we're only adding this particle, but we're not going to say that the electron or any of the particles that we're made of are charged under this particle. So how does it interact? So of course, in quantum mechanics, once these two particles have the same quantum numbers, they can mix. So if I produce a state, it could be the photon with an epsilon's worth. Apologies for not normalizing things to one, but with an epsilon's worth of dark photon. In the actual interaction, Hamiltonian, this goes under the name of kinetic mixing, because really this is an interaction of the kinetic term of the photon with the kinetic term of the dark photon. But in the Hamiltonian will be now just normal QED or normal optics, and an epsilon times our E field times their E field, and our B field times their B field. And this is allowed by all symmetry. Yes, Paul? Not entirely. Good point. So the longitude, so strictly speak, so then this goes well beyond the degree of detail that I can go into if we're going to get to. But so for example, a massive particle, you can go to the rest frame. This is a vector, so there's 1, 2, 3 degrees of freedom. Photon only has 2. So there's some rule. So in this basis, it's not very convenient to write down the mass. The mass is written much more conveniently written for the vector potential. So there's a mass squared a mu prime. And once you write down that and you write down the kinetic mixing, there are some selection rules about what can happen to a transversely polarized photon that would be produced in one of your lasers, but also how would the longitudinal polarization, the new polarization, be produced. So there's, yes, thank you for pointing to a can of worms that I will not quite open, but it is very much there. What this will mean, though, is that I will be sort of very loose, but in some equations I'll be more precise. The effective interaction between the photon and the dark photon is not only suppressed by this epsilon, it will also be suppressed by the mass of the dark photon, because of this fact that if the dark photon doesn't have a mass, I can rotate it away. So there will be a suppression of mass divided by the frequency of the lasers. But yes, in terms of rotations, they don't quite have the same symmetries. Just so you, okay, the colors are not coming out very well here, but just so you are aware, the dark photon is not a fad of mine necessarily. It's me as well, but there are many ways that a dark photon could appear in nature, and people have given a lot of thought as to what systems could constrain the existence of a dark photon. So often, again, apologies for the low resolution, but imagine a mass here, a mass axis on a log scale going to 10 to the minus 15 to 10 to the 6. So that's many orders of magnitude. And a coupling, which here is chi, but usually it's epsilon. Again, also many orders of magnitude. And a dark photon could be produced in many systems by the sun, horizontal branch stars, light shining through wall experiments that I'll allude to, the cosmic microwave background. There are many, many constraints, as well as this is a continuation of this plot, a zoom in that sort of lives up here, also sort of beam dump and collider experiments. G-2 of the muon, of the electron. So there's a lot of physics that could be related to dark photons. We're going to look around here at optical and below. So that's linear extension of optics. How about nonlinear extension? So now I'm allowed to introduce more than one field to an interaction. So it had better be two fields that I know that are part of the standard model, and let's introduce just one new dark field. And here's a way to do it. It's not the only way, but this is the popular way to do it. In particle physics language, this is the new field is called A, the axion, and it's F times F. It's F mu nu tilde. In sort of more pedestrian language, it's the axion is coupling to E dot B. Okay, so this is now a nonlinear. This is like the chi2 term that we had before with 3 E's. This is another term with 3 fields. One of them happens to be a B, so it's an E with a different polarization, if you like. And the axion. The axion is a scalar field, or rather a pseudo-scalar field, because this is odd under parity. And you can search for axions in many ways. Usually what you do is you turn on a B field, and then you look for linear mixing between the E and the A. Like the dark photon, again, a lot of experimental activity. These searches that are lines here, assume that the axion is the dark matter in the universe, and they're sort of systematically looking at very particular masses. Other searches include supernovae. The sun cast is an experiment that is actually looking for axions coming from the sun with a huge magnet. Again, a lot of activity. Yes. Mm-hmm. Yeah, so good point. So this is, again, a higher dimensional operator. This is not dimensionless like the epsilon of the dark photon. So this is a dimension full scale. Chi2 was also dimension full. Actually, Chi2 has a different mass. This is a dimension 5 operator in my language. I'm sorry, I'm not sure which language I should be using. But I'll use both and let's see what works. So this is a very small, weak interaction. Unfortunately, I would love it for it to be bigger, but all these experiments are there. So this 1 over F in another convention can be called GA gamma. And it has a dimension of 1 over mass, or 1 over energy. Yes. Right, so the field has dimensions of a field, dimension 1 in my language. E dot B has the same dimension as the Hamiltonian density, right? Yeah, this is also the Hamiltonian density. So the dimension of this had better be the same as that. So this has dimension 1. So it's an inverse GeV. This is a very small, so at the end of the talk, you will see what is the, so I'll ask the question. Let's say I build an optical system such that I have a photon that can undergo spontaneous parametric down conversion to another photon and an axion. What will the rate of that be? And then you can compare that to chi2. And it'll be orders of magnitude smaller, unfortunately. And I'm a bit frustrated by that, but that's, well, this is a very small interaction. It's a bit hard to, so I think the most apples to apple comparison will be to compare those rates. So again, this experiment, for example, or many of these, they turn on a big B field. And yes, they will just turn on a B field that's as big as possible for them. Put my, oh, is there a clock here? How am I doing with time? Oh, okay. Okay, ooh, I'd better hurry. But yes, you want to turn on a big B field. Actually, with spontaneous parametric down conversion, you do not need to do that. So that's one of the novelties. Okay, so I will skip this and let's start. This was a lot of introduction. Let's get to a little bit the meat. So again, I would like to have a pump produced a signal and an idler. So this is the standard model version, signal and idler. I'd like the idler to be either this axion or this dark photon. By contrast, other ways to look for these particles would be in the lab. And let's say I only want to search in the lab. I would construct a light shining through wall experiment in which I have a lot of photons on one side of the wall. Some of them would convert to one of these dark particles, and I would look for another one on the other side of the wall. So this approach would have the advantage that here I'm going to pay something small squared, both on this side of the wall and that side of the wall. Here I'm only going to produce, and I'm not going to try and detect the dark photon. I'm going to try to detect the signal photon that was produced in association. So this is a missing energy experiment. So this will scale like epsilon squared, not epsilon to the 4th. So this is the head start. But so it's going to be tough going ahead. Let's talk a little bit about phase matching or energy. So now we're going to try and speak both high energy physics and optics language at the same time, or energy and momentum conservation. So usually in optics, you phase match, which means you conserve the sum rule that has to do with energy. With momentum, in principle, you can construct any triangle you like if you have the full freedom of setting the indices of refraction for the initial and the two final state photons as you like. And this is one of the neat features. So for a particle physicist, this is already strange, the fact that you can control these things. But in fact, you go upstairs, you can do that. And you can have all sorts of non-trivial kinematic configurations for the decay of a photon to a signal and an idler. So what would need to happen for this to work with, if I replace an idler photon now with a dark photon, say, the index of refraction for a dark photon is 1. Right? This is not a small change to phase matching. This is a big change to phase matching. So if I were to draw the phase matching triangle This is what it is for SPDC. This is what it could look like for a dark SPDC. The index of refraction of the idelr is now 1. This arrow has shrunk by a lot. And of course, I cannot have a big opening angle of this triangle. Yes. It's a dark photon, so it barely interacts with electron. It barely interacts with the crystal. In fact, even talking about the index of refraction is not quite right. Really, what's going on? Oh, and I didn't write it down, so I'll write it down. The dispersion relation for a particle is this, right? It has a mass. It does not have it. So in some sense, if you turn on a mass for this particle, in some, and I apologize for saying that, this could have an index of refraction which is less than 1, in the sense that the frequency can be much higher than the momentum, which is the other way around for a normal photon. Exactly. So it's effectively 1 or less by, so if there was a mass here, I gave myself as much kinematic space as I could, and I turned the mass off, but it would be even shorter. Yes, you're right. So indeed, for example, here are two, so let's say I'm in the fully general case. I have a pump photon. I produce a signal photon at some angle and an idelr dark particle, a dark photon at a different angle. These two are related to one another. So the 2 degrees of freedom I have are the frequency of the signal and this opening angle. So the opening angle is like so. The frequency normalized by the frequency is on this axis. For normal SPDC, for some choice of random indices of refraction, this would be a relationship that we have. For dark SPDC, now this is a zoom in of that, I get different signal frequencies, different relationships to the angle. And again, this shrinks, this sort of half ellipse shrinks as I increase the mass. At some point, the mass will be so high that this process will not be kinematically accessible. Right? Certainly, if the mass is above the frequency, I'm not going to produce it. Now, for the rest of the talk, I'll focus on the forward case, just because you get a lot of material, you get to go through much more material as opposed to going sideways. And the rates, I think, will be higher. So now setting this angle to 0, I still have the handle of the frequency. So here is, if I pick indices of refraction that are inspired by calcite or by lithium niobate, if I have a pump of a certain frequency, the signal frequency will be somewhere on these lines. Notice that there are 2 branches to this process. So in one case, the signal photon is going forward and the axion or dark photon are also going forward. In the other case, the axion is actually going backward. Yes. I pick the pump frequency and then I solve the 1 to 2. Then I use energy conservation and momentum conservation, and so I don't get to pick it. Phase matching or energy conservation and momentum conservation pick it for me, but there are 2 solutions. For the forward case, if I open an angle, there's a continuum. What it turns out is that if the mass is 0, for any n signal that is bigger than n pump, I can in principle phase match. So, for example, a birefringent material, if the signal is 1 polarization, the pump is another polarization, I can get this process to go. Very good. So The interaction rates, well, the way to calculate the rates is to write down the Hamiltonian and go through first or second or whatever order in perturbation theory that you need to go to, use Fermi's golden rule, et cetera, et cetera. So everything is actually hidden in the Hamiltonians. So again, just to recap, this is the normal SPDC Hamiltonian. This is the standard model. For dark photons, if I want a nonlinear process, I need to bring the nonlinear, the dark photon is the linear extension. So the nonlinearity will come actually from here. I have to bring my own nonlinearity. For the axion, so the theory is nonlinear, but I will need a crystal for this process to happen for an axion because in vacuum, this is kinematically inaccessible. I cannot phase match. So I still need a birefringent but linear medium to get this process to go for an axion. Okay, some of the details of the calculation. So now I would like to expand these fields in creation and annihilation operators to sort of go through the process of calculating rates. So for particle physicists, this is a very familiar looking equation, except for these are not quite plane waves. So particle physicists, we always have this equation with plane waves here, and we just go about our business with that. For optics people, you never use plane waves because no lab is infinitely large. Rather, you have beams of lasers and Gaussians, etc. But still, so you can pick some basis for mode expansion and work with that. It's very, because I'm looking at the forward case, these mode functions for both the axion and for the E and B fields, it's very useful to factorize like so, just to pull out into the IKZ to keep track of the momentum in the Z direction. The Z direction is the beam direction. There are two, broadly speaking, ways of doing this working in the optics. One is to have it live inside a one-dimensional system, nearly one-dimensional, which is a waveguide. This can be of order a micron thick, and the photons just stay in there. In which case, these functions are just some very well localized field, which is the same along the Z direction. I'll use a Gaussian because Gaussians are simple. But if photons are in a bulk crystal, then you need to account for the fact that you cannot keep a light sort of perfectly collinear forever and ever. Beams disperse, so they're Gaussian. So this is a solution for the wave equation in field space, which is a Gaussian beam. And there's a relationship for sort of the beam waist, how thick it can be, and for how long you can keep the light focused. So this is called the confocal parameter. And there's a relationship between the waist, the momentum, and the confocal parameter. So now you take these expansions, you decide whether you're in a waveguide or in a bulk, and you plug these expansions into whichever Hamiltonian you choose to work with, and you get a Hamiltonian. Because at the end of the day, we're looking for one photon going to another photon and another field, either photon or not, then there's a sort of a unified treatment for the whole story. So this is the Hamiltonian for either SPDC or the dark version. So this phi I is either an idelr photon or a axion or a dark photon, whichever you like. So that's the creation operator for it. There's creation for signal, annihilation for pump. This e to the I omega t takes care of phase matching for frequency. And this, this overlap integral is where a lot of the action is, and that is sort of the mode overlap of the three modes that you picked. And that will lead to phase matching, to momentum conservation. The rest is just a sort of effective decoration to get the numbers and the units right. And this is sort of a map of how to plug it, depending on which process you want to go with. Yes. Hopefully, right. So for example, well, it depends a little bit. As a theorist, I would like to say, okay, I'm going to look for an axion. So let's assume that I have a perfectly linear birefringent medium. So then none of this, of course, nothing is perfectly linear. Okay, don't apologize. We need each other. Okay, in general, again, because the index of refraction of an idelr is 1.5, 2, and the index of refraction of the dark idelr, my idelr, is 1 or less, there will be quite a bit of difference in terms of the phase matching. So at least in this example, we took the same crystal with indices of refraction for the two polarizations. And we assumed, and you see that the relationships between angle and frequency are quite a bit different. Well, okay, I don't know what quite a bit different. If you can tell the frequencies of photons apart by a few percent, yes, they're quite a bit different. So yeah. Three numbers, the signal index of refraction, the pump index of refraction, and the idelr, which, so for me, that's not a number, that's 1 or less. Yes, you will need to keep track of the dependence of all of these on everything, including the frequencies, and et cetera. Oh, I'd better hurry. Okay, so sorry, I have this twice. Very good. One interesting subtlety that I struggled with probably much more than, but it was pandemic, so it was a lot of fun to figure this out while I was alone, is so for normal SPDC, if I do it in a waveguide, this wave function overlap along the waveguide grows with the length L. So the rate, the differential rate in my language grows like L squared. The total rate grows with the length, only the length, because the bandwidth shrinks. But for a bulk situation, there isn't this growth with the length of the crystal, because I only get this one point where, one region where I have focusing. So for the case of the dark SPDC, I can focus, so it's better to be in a waveguide in some sense. But for the axion or the dark photon will refuse to stay in my waveguide. So the axion and the dark photon are going to be bulk modes, no matter what I do. So do I get a growth with L, or do I not get a growth with L? So that was my pandemic project. And the answer is you do get a growth with L. And the reason is that still if the pump and the signal are waveguided, I can get emission of a dark photon into modes along the whole length of the waveguide. So it's true that this will not interfere with that because these are two different modes, but at least non-coherently, this will be additive. So the upshot is that the rate grows with L, but the bandwidth does not shrink with L in the usual way for SPDC. And I've convinced myself of this in two different ways. This is not an orthonormal basis, So but it's almost an orthonormal basis, but you can do this rigorously in a well-defined basis. And you get agreement between these calculations. The rates, as promised, are going to be small. So I'll just, this has a lot of information. So I'll point to some numbers to catch your eye. So let's be maximally kind to ourselves and get the highest rate possible that is still interesting. So let's say I want to look for a dark photon. Again, the rate, so here's the full expression for the rate in its full glory, grows with L. You get a higher rate if you focus the beams to a smaller area. So that's wonderful. And you can get, so you can get many down conversions multiply by some number that is actually horrendously small, which is this effective coupling, making some sort of assumptions about the amount of incoming power, the length of the system, the amount of time you're willing to run your experiment. So if I want to just set the best limits on a dark photon set by a lab, and I ignore the fact that there are limits from stars, so epsilon should be less than 10 to the minus 7. So that means if I take a watt of laser and put it in a centimeter of crystal, so this is very much a tabletop experiment, or maybe I take a milliwatt, but I take it in a centimeter and let it run 1,000 times in a circle, so that will give me the same effect. Then I will get 10 down conversions every day. So that is a very low rate compared to what optics people are used to. But this is a very high rate for my co-authors on this paper, which are people who look for dark matter in the bottom of a mine, right? So they they build detectors with dark counts of order 1 a day, 1 a year, et cetera, et cetera. So this is where the interface of optics and particle physics needs to come together. So setting new lab limits on a dark photon, I think, is doable. The other extreme, so axion numbers are always harder. So here, in order to get 10 a day, again, to set the best lab-like limit, I needed a kilowatt of laser in a 10-meter system. This is starting to get more serious. And again, if I want to beat astrophysics, it needs to be even more difficult. But just to point out, so this is 100 kilowatts in a 100-meter experiment. In DESI, in Germany, there is a light shining through wall experiment with optical lasers with an effective 100 kilowatt laser and magnets strung along 100 meters on both sides of a wall. So in terms of sort of the size of experiment, this is comparable to existing systems, but this is very different, right? Nonlinear optics along 100 meters is, well, you can get 100 meters length on a chip by printing small circles, etc. I'm severely out of time, so there are many little thoughts and subtleties that have to do with the intricacies of optical systems and detectors. I will skip those. So I'll conclude that it is not unmotivated that there may be new light particles that interact with photons. And if they exist, optic systems are maybe an interesting place to look for. So axions, nonlinear, or dark photons, linear extensions. And so it's fun to explore this interchange. I'll point out that these dark particles also could be in the initial state. For me in this talk, they were in the final state. But in this paper with Christina, we're assuming that it's in the initial state, and then it is the dark matter that you're looking for. Thanks. Yoni needs to get this microphone. Yes.
Thanks for a great talk. Questions?
Oh, more models. This is enough for now. If I think like an optics person, is it linear or nonlinear? Linear, I think it's pretty well. That's the dark photon is sort of the most reasonable possibility. For nonlinear extension, yes, you could couple to FF. I think that will only make things harder. Because one nice thing about E dot B is that you change polarization, and then if one of the challenges here you could ask is, okay, I have a watt of laser power, and in that, so that's 10 to the 19 photons per second, and then 10 times a day, one photon with a frequency that's 5% lower was produced. Now I need to filter out that watt and find that that single photon with good efficiency. I know of some experimentalists that say that this is not as crazy as it sounds. I'm sure there are some that disagree. So, but the fact that you switch polarization is yet another handle to distinguish the pump from the signal. So that makes me happy. But so I don't. Yeah, I would love to have photon going to photon plus 2 new particles, and then milli-charged particles, neutrinos, but the rates are sort of absurdly low. Yeah. Yeah, so this is something I thank you for alluding to something that I skipped. So for example, if you're looking for a dark photon, I'm looking in particular for as it turns out that the rate is highest to produce a longitudinally polarized dark photon. So if you, so again, like in SPDC, depending on how you orient your crystal chi2 tensor, there will be some, in some orientation, it could be type 2 or type 1, depending on here this is a type dark, where the idelr, the dark photon idelr, is longitudinally polarized. And usually in optics, you don't bother with the longitudinal polarization because it doesn't exist. So that also could be another way to get rid of a background that may be there from sort of the normal nonlinearity. You just orient the crystal in a way that such that normal down conversion does not happen, but down conversion into a longitudinal mode could happen. So there's definitely subtleties, but I haven't gotten very specific about, say, a specific material and how you would cut it. Yeah, that's a good point. So that's depicted in this cartoon here. Yes. That's always a question for almost any search that you have. So one thing is there's a very particular, sorry. For example, the phase matching. So the hypothesis that there is a dark photon, say with a mass that's 1% of the pump frequency, would tell you that this process will produce signal photons with this frequency and that frequency and no other frequency. So you would see very distinct lines in places that you would not expect. Now and these are functions now of the indices of refraction. So you would change the indices of refraction, say by changing the temperature, going to a different material. These lines should shift in a very particular way using that equation. That's what one example. So again, you're looking for a sharp spectral line that shouldn't be there. Yep. Testing. So are you? Yeah. So if I have, it depends a little bit on the parameters. What I drew here is this is the waveguide that I'm talking about. So if we're at a bulk setup, then SPDC and dark SPDC only happen in the focus of the beam. So something width W and length B. And that's all you get. In a waveguide of length L, I can dark SPDC to go throughout the whole process. Now, how many modes do I need to account for? So the ansatz I took is that let me imagine that there is a bulk mode for the axion, which has the same width as the waveguide. Let me pick the K for the wavelength of that mode to be the one that satisfies phase matching. So now I have a width, I have a K that gives me a B, a confocal parameter. So now I will take these modes and spread them 1B apart. So that is the number of modes that I can go into, and that will be now incoherent. Now I think you're asking what happens if I close this on itself. I have not done that calculation. But I would imagine, so if the radius, if the length of this microring or whatever is many more of these, then I think this is a reliable calculation. If the size of this is such that this B is enough to go around the whole ring, then I would need to revisit. But and do it in my head. It's a good question. Thank you.